Welcome back, students. Let's resume our discussion on section 1 of this notebook, vectors. We talked about vector quantity. Vectors must have magnitude and direction, and also it must follow algebraic rules. Addition follows from parallelogram rule. Scalar multiplication, the same thing except multiplying by a certain real number k to its magnitude. In this case, k value is so close to 0 that I don't really have anything here as purple. In this case, k value is 1.97, nearly 2, so the purple vector w is nearly double the size of the blue vector, same direction of course. Scalar multiplication does not change the direction unless it is negative and points for the opposite direction. We have components x comma y, and position vector, displacement vector, magnitude formula. We talked about all those. Now let's talk about vector addition and scalar multiplication. And there's a reason I stopped and talked a little bit more about parallelogram rule and scalar multiplication, because we are going to talk about the very same thing in terms of algebra now. What if we have component form? It turns out vector addition is nothing more than just adding up two components, x1 plus x2, y1 plus y2. And scalar multiplication is just adding up k to each component. Want a visualization? Well, the same picture we saw before. And this is a breakdown of the same picture. Let me see if I can put these two in the same viewing window. Excuse me, let me copy and paste it down here and try to see these in the same viewing window. Okay, so that's v1 plus v2 in component form, and v1 is blue, v2 is red. Now that's the typical geometrical definition by parallelogram, and this one right over here gives you a breakdown of the same picture. The middle parallelogram stay the same. Please look at this blue right triangle and this pink right triangle on top. You ought to find out what's the x-coordinate of this new point here, the sum of those two vectors. How do I get that? It's horizontal distance all the way from the origin, all the way from y-axis, and from this blue right triangle, x1, plus from this pink right triangle, x2. So this point is x1 plus x2. You can do the same thing with these two triangles. y2 plus y1 will be the new y-coordinate value. Also, you can just use it as a formula and simply memorize it. v1 plus v2, just add up the components. x1 plus x2, y1 plus y2. So natural that I haven't seen any students struggling in this vector addition ever. Just add up the components. Scalar multiplication, again, I've never seen a student struggling in this concept. Let's consider easier case first, when k is positive. Okay, just same direction and just magnifying. Oh, k is randomized again. Okay, alright. Okay, k is about 1.66 something. So if I just multiply by k, this is x. X is stretched by k, so k times x. That's y, and y is stretched by k all the way up there, and we end up with red vector. And that visualizes scalar multiplication in terms of component. And k is negative, red will go to the other direction. Okay, like this, going to the other direction. So if you have component, just multiply k to each component, and that's how you do scalar multiplication. Do you have some examples? Oh. Okay, looks like we'll have to do some examples of it later, talking about something else first. Standard unit vectors. There are some special unit vectors, special vectors I and j, and I and j are unit vectors. That means vectors of size 1 and pointing towards horizontal and vertical. In 3D we need I, j, and k. Where's the visualization, by the way? Is it here? Yeah, okay, alright. And we have a vector w, which is 3, 2, but I is this blue and j is this red, and then I go 3 times of blue, so 3i plus 2j, that's gonna go over to from here 0 to 3, 2. So w is x, y is the same as xi plus yj, basically. Here's a visualization of that. Excuse me, I had to cough a little bit. Those are standard unit vectors, just horizontal and vertical, but there are other unit vectors too, unit vectors pointing toward arbitrary direction. How do we get that? Just get a vector, any vector v, and then divide by its magnitude. If this vector points toward a certain direction and size is 2, divide by the size, so make half the size so that size is 1, and that's a unit vector in the direction of v. If this original has size 17, then divide by 17, then you're going to get the same vector in the same direction, but the size is 1/17 of the original, which is actually 1. And that's how you get unit vectors in that direction. We use this hat notation for unit vectors. These are all very, very simple, so let's do just a small number of examples and just move on. Here's an example. V is 2a minus 3b, and express it in component in terms of I and j, where a is I plus 2j, b is 4, -3. Well, let's do component first. In order to do the component first, everything has to be in components, so let's write this one as component. Oops. And here we go. A can be written, instead of I plus 2j, you can write it as 1, 2. And then calculate 2a minus 3b. Well, here it is, 2a minus 3b is nothing more than 2 times vector 1, 2 minus 3 times vector 4, -3. And just use the same algebra operation, multiplication first. So multiply all those coefficients first, double each coefficient, -3 times each coefficient, and then add everything up. We end up with -10, 13. Very simple computation. What if you use ij expression? Well, this one is written in terms of I plus 2j, so this one should be written in ij form as well. So instead of 4, -3, 4i minus 3j, alright? And then put those into 2a minus 3b form. Well, here we go, 2a minus 3b. This is a, isn't it? I plus 2j, and that's b. 4i minus 3j. And then we simply distribute coefficients and then take those like terms together, just like intermediate algebra, except for those vector arrow symbol. and then put those like terms together, and what do you get? Negative 10i plus 13j. Of course, the same as before. So these kind of algebra are really simple. I mean, they may have been inspired by geometric quantities and all the arrows, but in terms of algebra, really, really simple. How about the magnitude of this vector that we just calculated? Oh, this vector I mean, negative 10 comma 13. Well, all we have to do is plug those into the magnitude formula here, negative 10 squared plus 13 squared, and take the square root of that. So square root of 100 plus 169, square root of 269. Finally, find out the unit vector in the direction of v. All we have to do is get v and divide by the size, because v itself has a size of square root of 269. If I divide by square root of 269, the size will become 1. And that's it. Divide by square root of 269, and you're going to get, well, this one. And that's the answer. But if you want to express it in terms of ij form, well, you can take one extra step. Personally, though, I usually prefer those, not bracket, what do you call it? Triangular bracket or triangular parenthesis form. The coordinate form better, usually. But some people prefer ij form. I'm not going to prevent anybody doing this. These are really, really simple deal. Just a little bit of algebra, you can get used to these kind of things very quickly. I assigned several problems like this in Web of Science, so please take time to do these. Extremely, extremely simple deal. We're going to talk about dot products in the next segment of the video, and that too is very, very simple.